Thank you. I'd like to thank the organizing committee for inviting me. Thank you, Ulker, for this presentation. I'm honored to be among you guys here to present about the future of mesh implant and pelvic organ prolapse surgery. So what I'm going to do over the next 15 minutes, these are my disclosures, and pertinent to this talk, I'm the Chief Medical Officer for Colomedics, which is a spin-off company in Cleveland that's based on the work that we're going to present. So what I'm going to talk about, essentially, this talk follows through what you guys presented over the last half a day with the prolapse repair surgeries. So what I'm going to do in this talk, I'm going to review some of the major studies that were sponsored by the PFDN in the United States, and then see what were the take-home messages or results from these studies and how that inspired the work we're going to propose to do. So my previous speaker, Omar, did mention about the CURE trial and the management of urinary incontinence. I'm not going to go over this trial as much as incontinence is concerned, but the CURE trial was one of the first big trials by the PFDN in women who have pelvic organ prolapse, randomizing them for urethropexy with Birch versus no Birch, concomitant with the sacrocolpopexy. Why I'm mentioning it? Because I'm really interested in extended CURE trial, which is the 7 years data that was reported on the prolapse outcomes of this surgery. And in this, I don't know if you have a pointer here, in the last grid here is the actual new definition that they adopted when they reported this 7 years data. So of all the women that were randomized to urethropexy versus non-urethropexy, at 7 years, around 66 patients in urethropexy and 60 patients in the non-urethropexy arms were evaluated, some by physical exam and some by telephone encounters. So what they found, this is the data from the 2-year publication as well as the 7-year data. At 2 years, the surgical recurrence rate or the surgical success of the prolapse or the failure rate was around 9%. But when you look at the failure rate at 7 years, and this is based on the anatomical definition, it went up to 22 to 27%. And this is a very important point. I know we all like what we do. I do a lot of sacrocolpopexies robotically, but this is an eye-opener for me that there is a perceived and there is an objective data out there based on one of the longest trials by PFDN that shows a high recurrence rate objective by if you do a sacrocolpopexy. Yet, if you look at the reoperation rate, and this is in this grid here, the reoperation rate for mesh exposure, for recurrent prolapse, or for incontinence was low, around 16.7%. Only 1/3 of those was for recurrent prolapse, and 1/3 is for mesh exposure, which gives you a recurrence rate which is consistent with what my other colleagues who discussed this morning, around 10%. Now, the optimal trial is another study that was published in the United States, sponsored by the PFDN. And here in the optimal trial, this is a 2x2 factorial randomized trial, where patients were randomized to either behavioral therapy or usual care, and then there is surgical randomization for uterosacral suspension or sacrospinous ligament fixation. And here, I'm interested in an extended trial, optimal trial, that was published by my colleague Eric Jalovsik from Duke. And when you look at the outcome, the patient population here, there was 150 patients randomized to the uterosacral suspension and 138 randomized to sacrospinous ligament fixation, with the majority of the patients being, as we discussed earlier, stage 3 in this study. When you examine the surgical success of these procedures, you can see that at 2 years, 44% of the uterosacral ligament suspension and 45% of the sacrospinous ligament fixation failed based on the definition that we just discussed. But at 5 years, the primary surgical failure went up to 64% and 71%. So if you review this data at 7 years, at 5 years, you will see a higher recurrence rate than what we typically discuss in with our patients. But what's important is when you look at the surgical recurrence rate, how many of these patients went back and had surgery? It's almost 10%. So there is always a discrepancy in this reported literature between the anatomical failure that we see on exam in randomized clinical trial and the reoperation rate, or what is clinically valuable to the patient, being low. The third study which I will highlight is the SUPER trial, and this SUPER trial randomized women who have uterovaginal prolapse to mesh hysteropexy versus vaginal hysterectomy and uterosacral suspension, and followed the patients. And out of these patients at 5 years, you can see this is the outcome. So in the hysteropexy arm, you had a success rate of around 66%. In the hysterectomy arm, the success rate was around 51%. So obviously, when you reinforce the support with a piece of mesh, although mesh is essentially pulled out from the market in the United States and we're not performing any vaginal mesh procedures, there was a higher success rate. So reinforcing the support with a piece of material helps with the outcome. So this is a trial that we're currently conducting at University Hospital. We are the primary site. It's sponsored by the National Institute of Health. It's a randomized clinical trial. I'm just highlighting it here because more of these trials will give us more data. This is a premier trial which we designed for women who have uterovaginal prolapse, comparing their outcomes with vaginal hysterectomy and uterosacral suspension versus laparoscopic supracervical hysterectomy and sacrocolpopexy or robotic. So this will give us an answer if either one of these procedures is superior to the other at 3 years in our patients. We are enrolling into the study. We are a multi-center trial that we're doing in the United States currently. So food for thought. This brings us to where can we improve the field? Where can we move from here? So can we apply new biomaterial to augment native tissue repair? If so, can we learn from a demand study, which is a study that is also sponsored by the PFDN, looking at the MRI findings in patients who have failed to see where is the failure in the patients who have failed prolapse repair and identify areas of failure and how we can improve on our repair. Can we build on the work done with modeling? Eric Jalowski from Duke has done fabulous work on modeling to predict women who have prolapse. Can we incorporate artificial intelligence in that? So these are all food for thought for us to look into. And finally, can we innovate again, learning from our last experience with the vaginal mesh exposure? So this leads me to the next topic of my discussion is how do we innovate and where do we innovate? And my interest with my group is into a new biomaterial for prolapse repair. So obviously, man-made analogs for collagen is randomly oriented, it's loosely packed, and is very weak. On contrary, natural collagen is densely packed, uniformly oriented, and failure strength approaches bone. So can we improve on man-made analogs to improve alignment, packing, and cross-linking? So this is the work that was done by my partner and colleague. His name is Dr. Ozan Akos. I don't know if you guys are familiar with him. He's an engineer in Cleveland who's of Turkish origin. He's a brilliant guy. He patented this technology of electrocompaction of collagen. So when you take collagen solution and you pass it through this electrocompaction mechanism, you can create threads of collagen, and these threads are high density pure collagen aligned, and then you can put it on a spool and you can actually use textile machinery to fabricate this. So we can create more biomaterial from that. So we have done this and we created what we call colla fabrics. And colla fabrics is filament wound or knitted or woven. You can do whatever you want engineering-wise with that. It's the only load-bearing pure collagen fabric in existence. And this technology that we have developed now, we created a spin-off company, and then we have raised NIH and NSF funding that supported the work that we present today and tomorrow in the sling surgery. So this is the initial, when Ozan came to me and he said, Adonis, I have this technology where I can take collagen and make threads out of it. I said, immediately, this was in the era when mesh was a problem. I told him, can you make mesh out of it? And he said, of course. So this was the first study that we done together, where we took the collagen and we created a 1x1 Genapin cross-linked woven collagen. We had another one is EDC cross-linked woven collagen, and we compared it to proline and Xenamatrix for biologics. So we implanted them on the back of the rats, and we survived the animals for 2 weeks, 2 months, and 5 months. And then when we explanted these tissues, we tested them for mechanical properties, and we tested them for histology to see what's going on. So this is the results from the mechanical testing. And in this here, this is the Genapin cross-linked material. The Genapin cross-linked collagen, mechanical properties convert to the native tissue. So they're at 5 months, their mechanical properties equaled vaginal tissue or rectus fascia tissue in their mechanical properties. However, proline were also, their mechanical property were modulus were stiffer than the vaginal tissue, and that is the controversy and the problem we have with synthetic material in the vaginal tissue. It's stiffer than the vaginal environment that involves and leads to a high risk of mesh erosions. On the contrary, the EDC cross-linking didn't really work. At 5 months, the EDC cross-linking was very weak. So what we learned from this study is that the Genapin cross-linked mesh fared best in the mechanical testing. But look at the histology, and this confirms what we have all been talking about. Biologics in the vaginal space or even in reconstruction doesn't work, because when you looked at the Xenamatrix, there was no infiltration of that material by the host tissue. But when you look at the Genapin cross-linked mesh, there is new collagen infiltration between the collar fibers here. So these are the collar fibers, and all this pink area are new collagen being deposited in the interstices between the mesh. So obviously in the proline we have new collagen deposition as well, seen on histology. So this process appears as early as 2 weeks. This is a slide from 2 weeks. All this blue area are new collagen being deposited between the fibers of the collagen, bovine collagen that we implanted. Now, this led us to apply for funding, and we got a grant from the Ohio Third Frontier to do more large animal studies. So we did this, create through a filament winding process, a hybrid mesh, and this hybrid mesh was made from collagen in the middle, and the arms were proline, and we implanted them in sheep. Actually, we went and we did the surgery. We did the sling in the sheep, and then we harvested these animals at 6 months and 12 months. Obviously, at 6 months was the primary aim for us. When you look at the tissue here, this is the Lynx sling by Boston Scientific, and you can see the serration here at the end. And this is the collar sling, which is a hybrid sling at that time. This is the collagen part, and this is the synthetic mesh part. So when we did the testing, the collagen part of the sling here compared to the mesh sling, from a load perspective, the load was equivalent, and that load equivalence at 12 months was still there and better than the actual native tissue, rectus fascia or vagina. Once this study was published, we were able to create the Colamedics company, and then we started getting the funding. And this is the pivotal study in sheep, which we did a total of 10 sheep in Colorado. And we implanted them with the sling, and we harvested the tissue. This is the sling material at 3 months, and this is the sling material here at 9 months. What you can see here, and I'm not a histologist or a pathologist, but it's obvious that This is the urethra, and this is the mesh material here. There is no fibrous encapsulation, which is a very unique, important aspect of failure of biologics, is that there is no encapsulation. There is total integration of collagen within the intricacies of the mesh. And when you look here in the muscles, you can see that there is adherence of the tissues to the muscle itself, and there is no encapsulation. And this is one of the significant properties that we think that this material is promising for. So when you look at the data, and this is an abstract we submitted to the Society of Urodynamic Female Urology, currently under review. This is the, at 9 months, this is the material here. There is still some old collagen that we implanted. There is a new collagen deposited. And there is minimal inflammation, as you can read on the slide. But when you look at the mechanical properties, whether it is the tensile strength or the strain or the modulus, the strain and the modulus were equivalent at 3, at 6, and 9 months. The tensile strength went down, but it was still higher than the hydrated colasling ex vivo before we implanted it. So how does this, all of that research apply to prolapse? We believe that colofabric that we just described to you can potentially be tested to both augment native tissue repair and potentially replace sacrocolpopexy products in the future. And that's where our research is taking us. Maybe learning from the MRI, working with engineers a lot, you start talking like an engineer. When you talk to an engineer about the problem, they want to know where is the cause of failure. So learning from the MRI studies, the demand study that we talked about, hopefully we can understand more where is the weaknesses, where are the areas of failure, and design the products that we can address them. And success is always an important outcome, as you all know. But safety and do no harm should always be our North Star. And this is a guidance rule for us, that nothing that we hopefully would do in the future will impact our patients negatively, because what we're doing is trying to improve on their quality of life. Thank you very much for your attention.
Thank you, Professor Hijaz, for this excellent presentation. Please stay there. We may have some questions or comments.
Thank you.
Bir 15 dakika kadar gecikmemiz var. O yüzden Ömer'e soru almayalım. Ona dışarıda sorabilirsiniz. Ama Profesör Hijazi'ye soru varsa onu alalım.
Ben teşekkür ediyorum bu konuşması için. Türkçe sorayım.
Should I put my...
Konuşması için teşekkür ediyorum. Yayınlarını da takip ediyoruz zaten. Bu yeni geliştirilen meşlerin tekrar onay almasıyla ilgili hem FDA'den hem de Avrupa'dan siz bir sorunlar bekliyor musunuz? Eskisi kadar kolay olacak mı sizce? Yani bundan sonra yeni gelecek bir malzeme eskisi kadar kolay olarak gelecek mi? Bu hem fonlayıcılardan, yani söylediğiniz grantlere de başvuruyorsunuz. Onlar hasta görüşleri de istiyorlar muhtemelen. Hastaların bakışı nasıl? Ve diğer sorum da kolajen aslında bildiğimiz kadarıyla doğal bir malzeme ve degrade oluyor. Aslında beklenmez prolapsusta uzun dönemde kalıcı bir etki yaratması. Crosslinking yapıyoruz dediniz. O ne kadar etkili olur sizce? Teşekkür ederim.
Thank you very, very much for these questions. First of all, when you talk about the regulatory process, and it's going to be definitely a process that we have to review. It's going to be involves the FDA, obviously the European, for the approval of such a new material. I think we are not at that stage, not with prolapse. Now, tomorrow you'll hear where we are with the slings in incontinence. As far as the slings, when we presented all the preliminary data to the FDA essentially said this is a process, we call it 510K, but they need a clinical trial. So we are now in the process of applying for NIH funding to get funding to do a pilot clinical trial. And once that is done, we will proceed with the randomized clinical trial. For the prolapse, as I said, we don't have a product in mind at this point. We have a material that we have been testing in the incontinence in large animals. Hopefully, we'll have some outcomes in the pivotal pilot study in incontinence, which will open the door for us to use that in prolapse. Now, to your second question, which is a very important question, is how long that collagen material lasts. Obviously, we expect the material to degrade, and from our preliminary studies in the large animal, we see that this degradation is probably within 18 months the material will go. But what you could see from these studies is that there is a new collagen deposition within the material. And this new collagen deposition, to your question, is most likely because the cross-linking is pro-regenerative. And tomorrow I'll show you in the stress incontinence talk, when we did this initial study, we found that the Juniper cross-linked meshes induced M2 macrophages into the environment. So it's a pro-regenerative, and I'll show you tomorrow the work that we've done in a separate study on the M2 macrophages and their benefit in inducing the new collagen deposition. So yes, the collagen material, the biological, is going to disintegrate. What's exciting about this technology is that we engineer it. There is the cross-linking. The cross-linking is pro-regenerative. There is new macrophages, M2 macrophages that are attracted into the field. There is new collagen deposition. And when you follow these, at least at 1 year, we saw that there is good tensile strength in the material, and the material behaved like a ligament. And actually, now I'm removing my academic hat. I'm just putting my company hat on here. We are going into the orthopedic space with the pro-regenerative material and the shoulder repair and the ACL tears. So we're looking at that, and we have done some exciting stuff in that area. Thank you.
Başka soru? The last one.
First of all, congratulations for your inspiring presentation. I don't know if you can answer to my question, because it might be it might be a secret in your company, not yet published. But why our collagen in our native ligaments is not reabsorbed, and the ligament you produce artificially is reabsorbed? Where is the difference?
Well, I don't have an answer, not because I have secrets. I'm an academic guy at heart. I don't have an answer because I believe it's because when you apply the collagen in a form of an exogenous material that you put in our body, the MMPs in our body will just denature the collagen that is exogenous to it, versus the wear and tear in our system is made in such a way that if we injure ourselves, we heal, and sometimes the healing process induces new collagen formation that aligns itself. But as a foreign body, when you put a foreign body in your system, that foreign body, if it's not cross-linked, that's why we saw with all the biologics over the years. When I was a fellow, we were putting all these biologics for stress incontinence. 6 months later, they disappear. It's because of that process of denaturing. What we hopefully achieved here is that we engineered threads, and then the threads are engineered in such a way you can build them with to give you all the attributes of mesh, but with no complication of mesh. So we have the macroporosity, you can engineer it the way you want, and then the cross-linking, as I said, is key. Because when you put genopin cross-linking, you'll induce macrophages.
Thank you Profesör Hijaz.
Thank you.
Bu oturumu kapatıyor ve bir sonraki oturum için Tufan Tarcan hocamı kürsüye davet ediyorum. Hepinize teşekkürler. Bu saatte böyle bir katılım gerçekten gurur verici.